Hi everyone, I'm making this video about the addition of 3 particle spins because online I noticed there seems to be a bit of a void. Not a lot of people putting a walkthrough of this question. I actually couldn't really find a good one at all. Maybe I'm just bad at Googling, but anyways, nevertheless I decided I should make a quick video about it. Or maybe I shouldn't, but anyways, here we go. So the problem is we want to get the spin squared operators, eigenvalues and eigenvectors, and when I say spin squared, I mean the total combined spin for the 3 different particles squared. So just like this mathematically. Okay, so let's start by just expanding that. So that's s1 squared plus s2 squared plus s3 squared. Then of course all the ugly cross terms. So s1 dot s2 plus 2s1 dot s3 plus 2s2 dot s3. Okay, so as we can see, we're not just going to have the simplest time here. It's not going to be a diagonal matrix if we are to express the spin squared operators matrix in the uncoupled basis, because we have these cross terms and we know we can't know the spin of any of the particles. We can only know its spin squared and the spin component along any one direction. So first of all, let's just try to take care of these. Normally you wouldn't know what the heck to do with them, but thankfully from books you can see that there's this trick that you can take. So let's just go full in and go the 2 times the spin of one dot the spin of the other. It can be written as the z component of both, and in fact it's going to be 2 times the z component of both, plus we're going to bring in the raising and lowering operators. So we'll have s1 raising plus, times s2 lowering plus s1 lowering times s2 raising. Okay, and just recall, in case you forget, that the raising operator for spin is just spin x plus I spin y, and the lowering operator is just the complex conjugate. Oops, that's why. Okay, sweet. So let's just write out the whole spin squared operator. Okay, so I've written out the full spin squared operator in all of its glory here. So before you click away from this video and cry, don't worry, it's actually not going to be as bad as it looks. We're not going to have to go through all these all the time. And just a quick note, if the team at Drawboard, the app that I'm writing with right now, happens to be watching this video, which I'm sure a few of them will be, because this is going to be viral, your highlighter's not big enough. I mean, look at this, people. This is the biggest highlighter you can make in this app. Isn't that an outrage? Isn't that ridiculous? Anyways, okay, back to the problem. So the idea now is we want to know the eigenvalues and eigenvectors. So what we can do to get that is write out the the spin squared matrix in the uncoupled basis, and then we could diagonalize it, and that'll reveal the eigenvalues. And then of course, when you diagonalize, you also get the eigenvectors for those eigenvalues, and so we'll know the eigenvectors and their eigenvalues. Okay, so let me just set up that matrix. Okay, so here it is. We've got our 8 different kets written along as the columns, and we've got our 8 different bras written along as the rows. So of course, all the diagonal components are going to be the expectation values for the different uncoupled states, and then we're going to have all the cross terms. So let's go through and see what we get for this. So let's just start with the top left. Okay, so let's just walk through this. So spin squared for this, when all of the spins are up in the uncoupled basis, we're going to have spin squared is equal to each one of these. It doesn't matter which direction the spin is. S1 squared is always 3/4 h bar squared. So add the 3 up, we're going to have 9/4 h bar squared. And then hop along to the z components. Each one, this one's easy, they're all along up. So each one is h bar over 2. So h bar squared over 4 when you multiply them times 2, h bar squared over 2 times 3 for the 3 different terms, and you're stuck with 3/2 h bar squared. And all of these other terms don't matter. First of all, because they all include a raising operator, and these are all up to begin with. And of course, when you raise the highest state, it annihilates the state, it nullifies it. So, and also the other thing I was going to say is even if it didn't destroy the state and it just brought it to a different one, due to orthogonality, if this was different than this bra, you wouldn't get anything anyways. Okay, so this, when you add it, is 15 over 4 h bar squared, I think. Yep. So I'm just going to leave out the h bar squared, and we're going to have 15 over 4. And let's move on to the next one. So just looking at this next term here, where 2 are up, 1's down. The same thing, spin squared for the 3 never changes, so you have the 9/4 h bar squared. And then when you look at these, let's think about any way you can pick 2 from this. There's only one way you can pick it where they're both in the same direction. The other 2 ways, you're going to have 1 up, 1 down. So you're going to have 1 h bar over 2, and you're going to have 2 h bar over 2's negative. So you're left with this, and that gives you a 7/4 h bar squared. Okay, I'm about to erase it and put it right here, but one other thing before I do that is just notice, due to symmetry, I mean, you could think about it, you've just got 3 uncoupled spins here. It doesn't, no particle is special. So these 3 states, they should all have this along the diagonal, h bar over 4, or sorry, h bar squared times 7 over 4. So I'm going to put it for the next 3 diagonal terms. That should make sense, I hope. So 7/4 and 7/4. Try to align this right. It's confusing my mind a bit. Okay, and I'm just going to keep going with the diagonal terms for now, so let's move on to the next one. Let's just write it out. So you have the 9/4 h bar squared again. And nothing actually changes going from here to here. So the next terms, of course, were just thinking about the ways you could have 2 in the same direction. So you could have 2 in the same direction in one case when you pick the last 2. And that's going to give you a positive h bar squared over 2, because it doesn't, if they're both negative, the negative goes away. So you have the exact same cases over here. The other 2 ways are going to be negative because they're opposite, and then you've got the 2 along the same way, it's positive. So you're going to have again minus h bar squared over 2. And then for the next 3 terms, that means you're going to have the 7/4 again. Yeah, this eraser's kind of annoying. Okay, so 7/4. 7/4. If I'm talking a little slow, just watch this video maybe in like 1.5 to 2 speed, it might be better. Okay, and the last term, you're gonna have the 9/4 h bar squared, of course, and then they're all down, so each one is gonna be a minus h bar over 2. So you have minus 3/2 minus 3/2 h bar squared, and that is 3/4 h bar squared. Okay, cool. 3/4 h bar squared. Okay, we've got our diagonal terms. And let's just look at the first and last, and we'll see, like 15 over 4, you'll recognize that, remember for spin squared, that's going to be s plus 1 h bar squared. So in this case, if you've got 15 over 4, that can actually be written as 3/2 times 3/2 plus 1. And then similarly over here, this can be written as 1/2 plus 1. So these ones look pretty good so far. They seem to obey that. Okay, let me get rid of this. And then we can start looking at some of the cross terms. So, say we start with the top row, of course. Let's say we look at this one and we want to see if any of these raising or lowering combinations is going to put us into that up state. And of course it's impossible because you already have 2 up and just 1 down. So you've always got to flip 2 at the same time in this case. So you're never going to get up. It's just impossible. So this is 0. And it's the same logic for here, same thing here. You've got 2 down. So how could you ever flip 2 at the same time and get, flip 2 oppositely at the same time and get what you want. So 0, 0, 0, 0. And same going from this to any of these, actually the same logic. So 0, 0, 0, 0, 0, 0, 0. I really hope that makes sense so far. So what we see right now is, since this is actually diagonal in the first term, this first term is an eigenvector of our new coupled state. That's awesome. And the eigenvalue is this. Cool. Now let's look here. Okay, so just let me point out to state somewhat obvious. It doesn't really matter what any of these operators that actually leave the state intact are when we're trying to look at a transition. So we want this state to change. That's the only way. After you apply an operator, you need this state to turn into that state for it not to be 0 once you apply the bra. So we've got to look, are there any of these last 6 terms that are going to put us into this state? Well, we've got up, down, up. So what if we want to go to up, up, down. So actually, if you look at these last two, if we were to flip both of those at the same time, we would get up, up, down. So we need to look for one that raises 2 and lowers 3. Raises 2, lowers 3, raises 2. Aha, there it is. Okay, so cool. One thing to point out is a raising operator or a lowering operator. So S plus, let's say, to a state that is down. That's going to equal, I should just erase that. That is going to equal H bar times state up. Sorry, I'm going kind of slow here, guys. I gotta collect my thoughts. And S minus to up is going to equal H bar times the down state. Okay, if I'm remembering that right. I'm trying to think here at the same time, but yeah, I think this is right. So that means that it's just going to be H bar squared when we've got 2 of these operators at the same time, just multiplying those 2. So our one term is actually just going to be H bar squared, so it's just a 1. So awesome. What about this next one? Can this be flipped any way to get that? Well, we've got to flip the first one, and then if we flip the last one, oh, cool. So we can go up on 1 and down on 3. Up on 1, down on 3. There it is. Okay, so that's a possibility. So once again, the exact same thing is going to happen, and we're going to have a 1. And if you look at these next states, actually, it's impossible again. There's no way, and there's no way that you can flip up, down, down, 2 of them oppositely to get up, up, down. And same with any of these next 4. So these are going to be zeros. Okay, so cool. We then can just use kind of the symmetry argument again and come down to this row, and this should be a 1, that should be a 1, this should be a 1, and that should be a 1. Because remember, these states, you're just flipping 3 different particle spins in different orders. It shouldn't actually matter which is which, so due to symmetry, these should all be 1s. And the same thing's going to happen. There's going to be no way to do these ones, so these are zeros. Okay, cool. Now, if you look at up, up, down, is there any way to flip 2 to get up, down, down? No, it's impossible. 0. Same with these next 2. 0, 0. Just like these were impossible to go over here, these ones are all going to be impossible. So actually, we can just write 0, 0, 0, 0, 0, 0. And if I'm going too fast, you can just pause it and just think about a minute. Is there any way you could flip 2 of these oppositely to get, say, any of these? And the answer will be no. 0, 0, 0. Okay, now we're down here, and we've got up, down, 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 up, and down, up, down. So just 2 down and 1 up, different combinations. And so let's start over here, down, down, up. Is there a way to get up, down, down? Well, what if we were to flip the first and last? Aha, that would work. Okay, so there is going to be, of course, there's every possible combination up here. So this is once again going to be a 1. And then if we walk through these, we're going to see the exact same thing again for this next block. Okay, so you can just check that if you don't believe me. But yeah, you just keep getting the same thing. So I'll just fill in the zeros. And then, look at that. Our matrix, wow, this got kind of ugly. Our matrix is filled out. And of course, it's not diagonal yet. But the nice thing is, it is block diagonal. And so that means, since like, if you look at, let me get a different color, this block here and this block here, first of all, they're identical. So if we diagonalize 1, we've diagonalized both. I mean, we'll know how the different eigenvectors are. The eigenvectors combinations of these are going to be just like the eigenvectors combinations of these. Okay, so what we need to do is diagonalize one of these block matrices, and that'll reveal our eigenvectors. So that's the next job at hand. Okay, so to solve for the eigenvectors, And eigenvalues. This is just an eigenvalue problem, so it's just linear algebra. So you know that the matrix multiplied by your set of eigenvectors, it's going to have to give you is the eigenvalue times the vector. So you end up getting the equation that you've got the determinant of whatever your matrix was multiplied by a lambda, where lambda is going to be your eigenvalues, is going to have to equal 0. So let's just start by saying a equals 7/4 over lambda to make things easier, and plop that in and just solve this. Okay, so this is going to be just taking the determinant. It's going to be a cubed minus a minus a minus minus 1, so plus 1, plus 1 minus a. So you've got a cubed minus 3a plus 2. Okay, so I might be missing some easy way to solve a cubic, but one way I know is that you can try to guess one of the eigenvalues, or one of the a values here in this case, and sorry, this is equal to 0. You can try to guess one of them, and if you do that, then you can use long division to get the other two. So I'll just do my method real quick. Actually, yeah, I'll just write out what I do. Okay, so easily guess 1 is one of the eigenvalues. Just 1 minus 3 plus 2 equals 0 when you plug that in, which seems to me is right. And so now you can actually do long division. So we've got a minus the 1 root, and you're taking that and seeing how that goes into the full thing. So of course, the first two terms, it goes in a squared, and that gives you a cubed minus a squared. And then you subtract these, and you get minus 3a plus a squared. And so this one goes in again, plus a. Okay, and that'll give you a squared minus a. And sorry, I was supposed to add the 2 down here. And subtract that, and you're going to have, let's see, minus 3a minus minus, so it'll be minus 2a plus 2. And then, this will go into that exactly minus 2 times. So we've divided this, and now, so we know that a cubed minus 3a plus 2 equals a minus 1 times a squared plus a minus 2. Again, there might be a way faster way to solve this. Please let me know if there is. So this is a minus 1, then just factor this other one. So a squared plus a minus 2. What is that? Let's see. That is, it has to multiply to minus 2 and add to 1. So it's going to be plus a, well, it's going to be plus 1 and minus 2 again. So it'll be a minus 1 and a plus 2. Okay, cool. I think that works, right? Yeah. Okay, cool. So we factored this, and now we know then a equals 1 2 times, and a equals minus 2 1 time. And that's not our eigenvalues, because remember, we did a substitution. A equals 7/4 minus lambda, so lambda equals 7/4 minus a. So our eigenvalues are actually, lambda equals 7/4 minus 1, so 3/4 times 2, and then lambda equals 7/4 plus 2, which is 15/4. Oh, these look familiar. Awesome. Times 1. Okay, cool. We actually have our eigenvalues now, and now we just got to get the eigenvectors for them. And of course, you get the eigenvectors just from plugging these eigenvalues back into our matrix, our block matrix. Okay, just plugging these eigenvalues back in. The first one, you just get the one equation. It's just v1 has to equal negative v2 plus v3. And of course, you've got an infinite amount of solutions to this, and you can. The easiest thing to do is just to set, say, v2 equals 0, and then you get one eigenvector. Also by normalizing, you get the constant front. And then you can set v3 equals 0, and you get the other eigenvector. Of course, you don't have to do that. You can choose any orthogonal combination that works. But this is the easiest way to do it. I'm trying to think. I don't think orthogonal is the best word there. But anyways, And then down here, when you plug in your eigenvalue, you get this equation, and it's just an easy, they all have to equal the same thing. And so just normalizing, of course you could have any phase on top, but this is an easy way if you want to keep it real. This is what you get. So we have our eigenvectors. Of course, what does v1, v2, v3 mean? Well, going back to, say, the block, remember they're the same, but for the first one, v1 would be this, v2 would be that, v3 would be that, and for the second block, v1, v2, v3. Okay, cool. So now we can actually write out all our eigenvalues and their eigenvectors. Do that down here. So let's just start with the top ones. We had 15 over 4 was the eigenvalue. And of course, let's write that actually as, like we said earlier, 15 over 4. That was the 3/2 times 3/2 plus 1. So let's write the spin like that. So we've got one eigenvalue is 3/2, and that eigenvector is just a simple up, up, up. That is an eigenvector. The last one, it was down, and let's write this. So I might not be writing these in the best order, but we're going to have a 1/2, and that was down, down, down. So there's 2 out of 8. And then the last 6 we just solved for. So the first one, we have these two eigenvectors here. Those are corresponding to lambda equals 3/4, the eigenvalue of 3/4, which is again the 1/2. So we've got 1/2, and that is 1 over root 2, 1, 0, minus 1, 1 over root 2, 1 minus 1, 0. Okay, so, and those were up, up, down, up, down. Okay, so we've got 1 over root 2 times up, up, down, minus down, up, up, and then 4 is 1/2 again, and that is 1 over root 2 up, up, down, minus up, down, up. And 5 is 3/2. So that's the one we solved for right here. That was corresponding to lambda equals 15 over 4 again. So that is just the 1 root 3 times, oops, up, up, down, plus up, down, up, plus down, up, up. Okay, and 6 is going to be what we just had, except we're talking about now the second block. So this is going to be 1/2 for 1 over root 2 up, down, down, plus, or sorry, minus, let's see here, that'll be down, up, down, and 7, 1/2 again, and that is 1 over root 2 up, down, down, minus down, down, up. And then last but not least, you have 3/2 again, and that is 1 root 3rd. Sorry, this was a root there too. That's going to be all of them. So up, down, down, plus down, down, up, plus down, up, down. Okay, we did it. Cool. So we have actually taken this problem of 3 particles adding the spin, and we've solved for the eigenvalues and eigenvectors. Awesome. All right, so here it is. I hope that made sense. All right, thanks.